My name is Pam Cai, and I am a 2024 Arnold O. Beckman Postdoctoral Fellow at the University of Chicago. And I've been studying ways we can leverage biopolymers and charged interactions to create fully recyclable and biodegradable plastics to mitigate environmental plastic pollution. In recent years, plastic production has soared to astronomically high levels, with over 400 million tons produced annually. To put that into perspective, that's roughly the weight of all humans currently on the planet. In the US, only 9% of discarded plastic is recycled, which leads to significant plastic waste that pollutes the environment. And the largest contributing factor to the growth of plastics is single-use packaging. You might think if we simply increased our efforts to recycle plastic, we would get to a better place environmentally. This only works to a certain extent. Plastics like this can are made up of polymers or long-chain molecules. In plastics, these polymers tangle together. Think about the tangling of a plate of cooked spaghetti with no sauce. The entanglement between spaghetti strands means that when you pick up one or two strands, you end up dragging up with you more of the spaghetti. That entanglement is what gives plastics formed of these polymers elasticity and strength. And when plastic is recycled, it gets chopped up, and so do these polymers. These chopped up strands are then used to form a recycled can, but now because it has much shorter chains, the tangling doesn't happen, like in this bowl of cooked short pasta. If you pick up one piece, nothing comes along with it, and you're able to separate it out easily. This results in a plastic that is brittle and weak, and to combat this, manufacturers will add back in more of the pure long-chain polymers, creating essentially new plastic. Part of my goal was to find a way to create a plastic that was actually recyclable, meaning that the recycling process didn't chop up the long-chain molecules. And there is a way that we know how to do this, and it comes from what we know about charged polymers, or polyelectrolytes. These charged polymers have either positive or negative charges spaced out along the chain. If it's a positive charge, it's called a polycation, and if it's a negative charge, it's called a polyanion. And there are many different charges that can go on a polycation or polyanion. For example, if the polycation has a positive charge that goes away with change in pH, then we categorize this as a weak polyelectrolyte. It's weak because the charge groups aren't always charged, and so it can't always attract a negative charge. And when we mix two oppositely charged weak polyelectrolytes together, parts of the polyelectrolyte chain will not be able to ionically pair with a long-chain molecule of the opposite charge, as shown in the diagram, where the two chains aren't fully touching. This means there's more room for salt or water between chains, and the chains don't tangle well enough to give the resulting material strength. On the other hand, we can have strong polyelectrolytes, which are basically always charged, and so they always want to find the opposite of their charge and ionically pair up. And so when oppositely charged strong polyelectrolytes are mixed together, they drive the system towards a highly tangled polymer-rich solid that's compact and mechanically strong. Another avenue of growth in combating plastic pollution has been in the making of biodegradable or compostable plastics to replace petroleum-derived plastics, such as polyethylene, polypropylene, or PET. Polylactic acid, or PLA, is one of the most popular compostable plastics on the market because it was shown to completely degrade. But the caveat is that this complete degradation can only happen in industrial composting conditions. If PLA is left in an average person's backyard compost, the PLA retains its shape and undergoes almost no degradation up to 6 weeks. Considering that not many compostable plastics are sent to industrial composting facilities, they essentially end up contributing to plastic waste in landfills or oceans. The use of plastics across numerous industries necessitates reimagining their synthesis and sustainability. I combined the above concepts together to develop a new material that would address the downsides of our existing paradigm. Firstly, we want something recyclable to reduce waste in the environment, and so I leveraged the ability for polyelectrolytes to be recycled without reducing the length of the chains. To begin, we have solutions of oppositely charged polymers, and since they are charged, we need enough counterions to surround the charged polymers so they are effectively neutral. You can see that the polycation with 6 positive charges also has 6 negative counterions. When we mix the oppositely charged polymers together, the change in entropy drives the separation of a polymer-rich solid phase out of solution. This is because entropy is related to the log of the number of microstates in a system, And the number of microstates in a system is directly related to both the number of orientations each molecule can have and the number of molecules in the system. And there are many more counterions per one polyelectrolyte due to the number needed to keep each polyelectrolyte neutral. So when these counterions are released, each of those increases the effective number of molecules in the system and thus the number of microstates. So thermodynamically, it's favorable to release these counterions so that we get to a higher entropy state, and this results in the polyelectrolytes collapsing onto each other and forming a solid phase out of the liquid. That solid material can be formed into a bag or a container, and after its use, thermodynamics dictates that by adding an excess amount of salt or ions and water, we can reverse the solid formation where the salts actually screen the charges on the polyelectrolytes, thus making them neutral and not so ionically attractive to each other. And this brings a material from a solid in a liquid solution to a pure liquid. And we can repeat this cycle for full recyclability of the solid material without changing the length of the polymer chains. Secondly, we want the material to be environmentally friendly and not rely on petrochemicals. So I decided to use biopolymers as the polyelectrolytes because they're naturally derived and possess inherent biodegradability. I chose chitosan, which is derived from crustacean shells and fungi, and alginate, which is derived from seaweed. So first, I tried mixing alginate and chitosan together, thinking that their charge groups would help me form the solid polyelectrolyte complex seen in other polyelectrolyte systems. But the solid-liquid phase separation never occurred, instead giving me liquid-liquid phase separation. And I tried drying off residual liquid, but the remaining material was very flimsy and had the consistency of tissue paper. So this one was not strong enough to replace plastic. So I made some modifications, and here I'm hypothesizing by changing the charged groups that are on alginate and chitosan, I can get that solid-liquid phase separation. And it did happen, and also the resulting solid part gave me this strong, transparent film. It looks very plastic-like. I formed these films by taking the solid out of solution, pressing it into a film between two heated metal plates, and letting it dry. After use of the film, the material is fully recyclable by placing the material into salt water, where it will fully dissolve into the liquid, and then pure water is added to dilute the solid concentration and drive solid-liquid phase separation once again. The bottom solid phase is then repressible into a new piece of plastic. Here you see the picture of what the material initially looks like after first formation and also after 2 recycles, and the white stir bars are around the size of candy, so one could imagine a potential application might be single-use candy wrappers. A concern I had with the dissolution recycling method was the amount of material lost to the solution during each recycle. So I measured the mass before putting the material in salt water to dissolve, and after it had been formed into a new piece of plastic. On average, over 6 recycles of the same material, 98% of the initial mass that was dissolved was retained by the recycling process, and the composition of the plastic was consistent throughout, with around 3 to 5% salt, 15 to 20% water, and the remaining 75 to 80% polymer. Given that plastics must hold up in applications like packaging, it's important to characterize the mechanical properties of these biopolymer-based materials. Here I'm showing the elastic and viscous moduli, which are metrics that denote the stiffness and fluidity of a material across 2 decades in frequency, and for reference, I'll also put here the ranges for elastic and viscous moduli of commercial polyethylene. The biopolymer PEC exhibits a modulus within the range of what polyethylene exhibits across 6 recycles, and not only that, the material behavior is retained across multiple recycles and up to temperatures as high as 100 degrees Celsius. One thing that really struck me years ago was the sheer size of these large floating islands of plastic in our oceans, the most polluted one being the Great Pacific Garbage Patch that's twice the size of Texas. How do we avoid that? Well, it turns out this biopolymer PEC currently can dissolve at around ocean salinity. If we convert ocean salinity to sodium chloride concentration, which is what I'm using here, it's around 0.6 molar sodium chloride, and at that concentration, we find that the PEC fully dissolves into the salt solution. And since the basis of these materials are polymers derived from ocean organisms like seaweed and crustaceans, it's likely that the ocean microorganisms have the capabilities to break down the dissolved biopolymers. To verify this, I measured the degradation of the alginate component of the biopolymer PEC material by an enzyme called alginate lyase, which can be found in ocean organisms. The test measures absorbance over time, with greater absorbance indicating a greater degree of degradation. After 48 hours of incubation with the enzyme, the modified alginate was degraded just as much as the unmodified natural alginate. In conclusion, I developed a new sustainable plastic alternative out of biopolymers alginate and chitosan by modifying them to form solid polyelectrolyte complexes. And this biopolymer PEC material is processable into thin transparent films, are fully recyclable without chain shortening, and exhibit mechanical behavior similar to polyethylene thin films. All of that being said, the actual transition away from petrochemical-derived plastics and the mitigation of plastic pollution in our environment requires much more than just scientific advancements. In particular, we need concerted efforts in policy reform, infrastructure alignment, and consumer behavior, to name a few, to truly achieve sustainability. I am deeply grateful to my lab mates in the Terrell Lab, to my mentor, Professor Matt Terrell, and to the Arnold and Mabel Beckman Foundation for their generous support and encouragement throughout this work. Being part of this remarkable community of scholars has been both an honor and formative experience. The Beckman Symposiums especially offered meaningful dialogue, fresh perspectives, and insights that have enriched my development as a scientist. Thank you.